Hey, hello. All right. Welcome to class, folks. We're in the middle of the Sylow theory journey. Probably the most important. Oh, tropical geek is teacher's pet. Awesome. Cannot do anything wrong today. So we're in the middle of Sylow theory, which is probably the most important part of the traditional topics in group theory, the theory of finite groups. Okay, so that's where we are, and class should read chapter 24 this week. Okay, so let's continue with the proof of the first Sylow theorem. First thing I'll do, and then we'll talk about an exercise. And then that. Okay. And then we'll talk about we'll move on to the second Sylow theorem. Second of 3 Sylow theorems. Okay. So what's the first Sylow theorem? Let me state the let's look at the setting. Setting is G is a finite group, and P to some power is the largest power of a prime P that we're sort of focusing on, dividing the order of. All right, so let's say we are in this situation. We have picked a prime that occurs in the prime factorization of the order of G. Then a Sylow subgroup, remember a Sylow subgroup, a Sylow P subgroup, just means a subgroup of order, a P group of maximal possible order. Okay? And the first theorem says this. Sylow P subgroups exist. All right. And we were in the middle of the proof of this theorem. So the proof was, it was some inductive argument on the size of G. So it was the proof was induction on size of G. There are 2 ingredients, and then the second part of the proof, second ingredient was pass to quotient idea. So we're in the second part. So we've done some stuff which I ask you to watch the previous lecture. We had come to a conclusion. We had come to a fork in the road. We were allowed to assume that P divided the center of the group G. Right? So we're not saying that this is true about an arbitrary group. It was just that in the argument, in the proof, we had gone through some cases, and not a case, but we could assume that P divided the order of P divided the size of the center. Okay, so that was the structure of the argument got us to this supposition. Okay, not that this is always true. It's just that in this case, in this argument, we ended up here. And so in particular, there exists an element such that g to the p is which has order p. Okay. Awesome. Okay. Okay. So that's the conclusion we'd arrived at. And now what I'm gonna do is I'm gonna pass to the quotient by g. All right. So now consider the quotient. And whenever I talk about a quotient, I usually think about the quotient homomorphism along with the quotient group. Okay, so that's, I recommend that. Okay, so it's a quotient map that sends an element to its left coset. Okay, so consider the quotient map. What do we know about the quotient group? Now, what we know is that the quotient group is this number. Okay, the quotient group has order this, which is strictly smaller than g. Okay, this is smaller than g. So by induction, by inductive hypothesis, this group has a Sylow P subgroup. Of order, maximum affordable. So of order p to the k minus 1. See, because p to the k minus 1 is now the largest power of this prime that divides the order of this smaller group. Right? Call it h bar. Okay? That's the inductive hypothesis being used again, right here. So now what will we do? Now we do something really, really traditional when you're in the quotient situation. So now what? Now, let h be the preimage under the quotient map of this h bar. All right, so simply take the preimage of this group h bar. That's another group. That's a group in subgroup in h in G. All right, so what do we know about the order of h? So this is something to learn in quite generally. So what do we know about the order of h? Well, we know that the quotient homomorphism, when you restrict it to h, is a map from h surjecting onto h bar. Okay, so that's the that's all. Whenever you take preimage group, you can think of the homomorphism only restricted to that preimage, and you get a homomorphism from the h to its image, h bar. It's surjective by definition of preimage. Okay, so we have this surjective map from h to h bar. And what do we know about the kernel? Well, the kernel has to be this cyclic subgroup that we started with. Why? Because the cyclic subgroup is definitely contained in H, since Q of this cyclic subgroup is simply the identity element, E bar, in the quotient map. So, and E bar is contained in H bar. So the original kernel of the quotient map is contained in this restricted homomorphisms kernel. All right? And the kernel can't be any bigger. And so this is true, and kernel of can't be any bigger, since the kernel of Q is G. All right? So the kernel of this homomorphism is simply the cyclic group G. Okay, so now we know everything about the size of the... So now we can conclude what the size of the group capital H is. The size of capital H is the size of the kernel times the size of the image. The image is H bar. And the kernel is the cyclic subgroup. All right? So there you go. We've produced a subgroup of size p to the k, which was the objective. All right? So, in any group where p divides the order, k times p to the k, you will always be able to find a subgroup of size p to the k, a Sylow p subgroup. They exist. Great. Let's move on to the second thing now. The second item for today is a little exercise. And the little exercise is going to be, if you study what happened here, where I took something in the quotient, I took preimage and I considered the preimage subgroup. That trick is the only trick that's needed in this little exercise. A little exercise. Okay. So what's the setting of this exercise? We're going to use this exercise in the future. Okay, so here's the setting. Suppose K inside of G is a Sylow P subgroup. Okay. Then what can you do? You can, anytime you have a subgroup, you can take the normalizer. Okay? So remember, the normalizer always, of course, contains the original subgroup. And the original subgroup is normal in the normalizer. That's kind of the point of the normalizer. So now here's the exercise. Suppose if G is an element in the normalizer, okay? If G is an element in the normalizer, which has order a power of p. Remember, there's a prime, yeah? If G is some element in the normalizer of the Sylow p subgroup, which has order a power of p, then G is actually contained in the Sylow p subgroup to begin with. So just to phrase it oppositely, there are no elements in the normalizer outside of the Sylow p subgroup which have order p to some power. There are none. All the elements that have order p to some power in this home are actually in the Sylow p subgroup. And the hint? Oh, thank you, Alec. Okay. So the hint I want to give you is consider the quotient homomorphism. And look at what happens to G. So consider this situation. What do you know about the image of G? Maybe you know something about its order. Then lift it back and violate the fact that K was a Sylow P subgroup. There is no higher power of the prime. There's no group of prime power order that's bigger than K, that contains K. K is maximal among prime power subgroups. Power of P groups inside of G. Okay, it's the largest possible size. So that's the hint, and I'm going to leave that. I'm going to put this in our this week's homework. This exercise. Okay, so but we can understand the content of the exercise. It's just that you can guarantee that everything outside of the Sylow P subgroup, but inside the normalizer, cannot have prime power order. Great. Okay, so now I want to just state the second Sylow theorem. Let's state the second Sylow theorem. Let's state this. The second theorem says that we're maintaining the same setup, fix that same prime. Okay. Any subgroup which has prime power, which has order, a power of P, is actually contained in some Sylow P subgroup. All right, so that's what the second theorem says. The second theorem says that anytime you find a little subgroup of P to some power size, you can upgrade it to a Sylow P. You can grow it to a Sylow P subgroup. It's not saying that you can grow it in a unique fashion, by the way. There might be many different Sylow P subgroups that contain a given smaller P subgroup of a group. Okay, it's not, there's no uniqueness statement. It's again an existence. It's that you can upgrade any P subgroup to a Sylow P subgroup and enlarge. Okay, so now I'm gonna, before we talk about this, the proof of this theorem, I'm gonna tell you the basic strategy in the underlying the proof of both of the next two Sylow theorems. So let's look at the basic game. The basic game behind the next two Sylow theorems. All right, so let me show you this game, the setup. So the first step is usually this. Draw up one Sylow subgroup, which we know already exists from theorem number 1. Okay, so draw up, choose one Sylow subgroup. Okay, then the next step is to write out all of its conjugates. Create the set I'm gonna stick with the notation in the book. Create the set of all conjugates of this subgroup. Of all conjugates all right, so in other words, consider the action of conjugation of the group G on subgroups. And look at this particular Sylow subgroup and look at its orbit under conjugation. Okay? The orbit of this one Sylow subgroup. And we can pretend K1 is K itself. So K, GK, G inverse, and then another GK, G inverse here, and another one. All the distinct conjugates, put them in a set, C. All right, so the third move, in the third thing that all of the theorems will analyze. The third thing is to analyze action of conjugation not by the group capital G necessarily, but consider the action of conjugation by some particular subgroups. And this particular subgroup will depend on the theorem that we're trying to prove. All right? So this is the context of the proof for both Sylow theorems. Notice that it's like orbit stabilizer situation, group acting on some set. Notice how powerful, how far-reaching that simple idea is. It's the key trick in the proof of all the Sylow theorems, of these two remaining Sylow theorems. Okay. So, one thing to keep in mind, because we're going to act by conjugation on this set of conjugates of a particular Sylow P subgroup, one thing to remind you, here's a reminder. If you have a subgroup, H, if I don't want to use H or K, but here I'll just use H. If H is a subgroup, then the number of conjugates is simply the size of the group G divided by the size of the normalizer of H. This is because the normalizer of H is the stabilizer of the element H, where I view H is an element in the set of all subgroups. And I'm just doing orbit stabilizer. This is the orbit of conjugation acting on this set, on the set of subgroups, and this is the stabilizer. So orbit times stabilizer is the size of the whole group. All right, so we know how big this subgroup is, in other words. Okay, great. Let's see here. Okay, let's now start the proof of the second Sylow theorem. Okay, so what's our context? The second Sylow theorem says any subgroup of prime power order has to be is contained in some Sylow P subgroup. All right, so that's what the theorem says. And so let's begin its proof. Suppose we have this subgroup. So its order is some prime power of p. So some power of the prime p. Okay. Let's look at the action of H on the set, the conjugation action of H on the set C. Okay, so I've chosen a Sylow P subgroup K, which I can do by theorem 1, and now I'm looking at the action of only H, not of the whole group G, but only the subgroup H that I'm claiming is contained in some Sylow P subgroup. Okay? Okay. All right. So, what do we know? What do we know? We know the following. We know that the orbits of this action have to have size either 1. You can have an orbit of size 1. Right. Or what we know is the orbit is a power of, has size a power of p. Why? Because H has size a power of p. And the only numbers dividing a power of p are other powers of p. So a non-trivial power of p. Okay, so the first thing we have to deduce, in the proof is to show that 1 has to occur. Okay, the first thing we have to prove is that 1 must occur. i.e., there has to be a fixed by conjugation by H. Okay, so let's think about this first goal. Okay, so let's wait, but I'm now blanking on how to do this first goal. So wait. For me, so that I don't ruin my life, for me, let's assume that we know that there is a orbit of size 1 so that you understand why I'm trying to prove this in the first place. So let me do that first. Okay. So why is this, why will this give us what we want? This will give us what we want because right. This will give us what we want because if conjugation by H leaves some ki invariant, some ki fixed, then what does that mean? That just means that H is a subgroup of the normalizer. Ah, yes. H is a subgroup of the normalizer. But now, what kind of a group is H? H is a P group. Okay? And so every element in H has order a prime power of P. A power of the prime P. A power of the prime P. And now we use the exercise. That's right. We use the exercise. Where's the exercise? Little exercise. When you have a Sylow P subgroup, you look in the normalizer of it. You're not the only power elements whose orders are powers of a prime P are the elements in the Sylow subgroup. So you apply that to H, to elements of H in here. So the exercise gives that H is contained in Ki. Yeah. Okay, so that's why we want the first goal. We want to deduce that there's some orbit which is size 1. Great, good. So now let's go look at the first goal. Awesome. Now that you understand why I want to do this, why I want to deduce an orbit of size 1, let's actually show that there must be an orbit of size 1. So let's assume. Now, assume that there are no orbits. Of size P, of size 1, when H acts on the conjugacy set via conjugation. Okay? But then every orbit under this action has size divisible by P. Right? Okay, but then the number of elements in this set is divisible by P. Right? Okay. However, now let's look at orbit stabilizer for the group G acting on C. For the whole group G acting on C by conjugation. Of course, the only actions here in the Sylow theory will be conjugation. Okay, now look at the orbit stabilizer situation for this. Okay, C is one orbit. And what that means is that the size of C times the stabilizer of one of the elements in C equals the size of the group G. right? Orbit stabilizer. But what is this stabilizer? Stabilizer of a subgroup under conjugation. This is, let me scroll back and show you. This is a reminder. If you have a subgroup, then the stabilizer is simply the normalizer of that subgroup. Okay, so this is the size of wait, but hold on. I'm trying to derive a contradiction. Hold on. So we know that C, size of C is the size of this times that. So how do I conclude though? How do I conclude? Wait a second. I thought I had it, but hold on. The size of C is one orbit. We know we're pretending that the size of C is divisible by the prime P. I was gonna... Oh. Okay. Ready? Okay. We have that the size of C is divisible by the prime P. So this part, we know, is divisible by P. We know that G is divisible by the P to the K. That's the largest power of prime. Okay, but then, this thing is divisible by at most P to the K minus 1. But this is absurd. Because K is a subgroup. And the size of K is Sylow. Size of K is P to the K. This already has... So that's absurd. Okay, so that's why this orbit can't be the size of this conjugacy class of conjugates of K can't have size divisible by P. That's actually something quite general. We just learned that quite easily. That if you take a Sylow P subgroup and you take all the conjugates of it, the size of that set can't be divisible by P. That's just some simple, in retrospect, simple observation. Okay, so let me just say what the conclusion was. The H action on C has to have a singleton orbit. But then, by the exercise, H is contained in that Ki. Phew! I barely got through the second Sylow theorem. That's embarrassing. Okay, so we now have it. Every time you take a P subgroup of a group, you can upgrade it to a Sylow P subgroup. That's the statement of the second Sylow theorem. Any subgroup which is a P group can be upgraded, can be inflated to become a Sylow P subgroup. So now I'll state the third Sylow theorem. Third Sylow theorem. And this third one is used the most. The third one is used absolutely the most. All right. And I think this one was proven in like 1879. Right? So it's old. So it's very embarrassing that I can't remember the proofs of Sylow theorems easily. Okay. Okay. Third Sylow theorem states 1. Every Sylow P subgroup is conjugate to every other. All Sylow P subgroups are conjugate to each other. There's only one orbit of Sylow P subgroups. 2. The number of Sylow P subgroups, let's call that number n. Satisfies n is congruent to 1 mod that prime. That's curious. And 2, n divides the order of the group. Okay, so we have a lot of information, in other words, about the number of these maximal sized P subgroups of a given group G. The number is constrained. See, all of them are conjugate. First, we also know that all of them are conjugate to each other. That's sometimes useful. And also that the number of them is a number that's 1 mod the prime and also divides the group G. So it really is just like a finite list of possibilities. Okay, so let's look at some easy parts of this theorem and set ourselves up for the actual content. The proof of this theorem will feel similar to the proof of the last theorem. It's similar. Okay. So if you know 1, then 1 implies that by orbit stabilizer. 1 implies that. You see that? That's pretty clear. So if we can show that all of them are conjugate to each other, that would be great. And I think that's the first thing that I'll show. But this one is kind of curious. This is kind of curious. At least that's my opinion. So the fact that it's 1 mod P seems like a really awesome statement, but what we will find is that this trick that we used in the proof of the second Sylow theorem, where the inclusion of H inside of some Ki was equated with there being a singleton orbit. That equivalence is what explains this n is congruent to 1 mod p curious condition. Okay, so that's what I'll prove on Wednesday. That will conclude the proofs of the Sylow theorems. And then for the rest of the week, we will just continue with actually using the Sylow P theorems to show you that with Sylow P theorems, all that stuff I did last week where I did flower theory, case check, analyzed groups of order up to 60, lots of it becomes way easier with the powerful new tool of Sylow theory, the 3 theorems of Sylow theory. And with Sylow theory, we'll be able to prove why the only group of order 60, simple group of order 60, is actually A5. Sylow theory will help with that kind of a proof. So that's what we'll do after I prove the third third fundamental theorem of Sylow theory. Okay, so class, review the game. Review the game that I talked about in the first part of, in the sort of middle part of the class this time. Review this this discussion. Where is it? Yeah, this basic setup and basic game. Review that, because that's what we'll use again for the third Sylow theorem. So if you get comfortable with this, you won't be so scared of the proof of the third Sylow theorem. Okay, and that's what I'll start with next class. Great. Okay, now I'll look at that, or if there were. Yes, Pro? Oh, thanks Raven for following. We love proof days. Proof days are proof days are interesting, I'd say. I actually don't know. You know, when I look back at my experience taking math classes as an undergrad, I'm not sure if there's ever a proof of like a main theorem in math where the professor did it and, like, you know, they explained it and then I was like, whoa, like, and it like stuck with me. What I do remember though is Professor Serganova going through all the groups of size this and showing that you always had a normal subgroup. Those things imprinted in me, but I never really learned a proof of a main theorem from the class, from the lecture. The ones that I know, I learned from reading. So like, I kind of am curious if that's something other math professors agree with. I don't know. Especially with the advanced classes, like, how much do you gain out of lecturing a proof? If you can boil the proof down to like important principles like this game, or like start giving names to ideas like induction on G, pass to the quotient, I feel like that's probably a more effective thing to talk about than just like going through the proof line by line and executing it. So I do some kind of weird hybrid. But yeah, this game is really fun to play, and part of the key is the simple little exercise here that makes a lot of this tick. But this exercise is easy, for sure. Actually kind of one line. So students think about this exercise. What am I talking about? I am. I'm just talking about. No. Non-math majors rarely take this class. Crow. I think. Well, no, definitely there are no non-math majors in our class, but I think maybe some computer science people might take abstract algebra. But beyond that, oh, actually, maybe some physics people might be interested in abstract algebra. Though, yeah, I think sometimes you get some physics students in abstract algebra classes. But because the physicists need to, I think physicists need to know group theory. So yeah. Though I don't know if they ever need to know finite group theory. Really, I mean, I don't know if they need Sylow's P subgroups. I would say that they need to know Lie groups probably. Oh, you need 2 math classes for a math minor? I'm not sure which 2 would be cool. Hey Crow, have you let's assemble the credits while I'm talking to Crow. Here's the credits for. I'm trying to make a habit of assembling the credits. The Tropical Geek was teacher's pet, so they're on the top. You know, Crow makes it just by sheer capitalism. Okay, but Crow, do you like proving things? Do you like math classes? So does discrete math count for you, Crow? Does that count, or does it have to be more advanced? I don't know. Then there's who else was critical? Probably credits. Okay. Credit my memory. Barely get. What else? Okay, I already took discrete math, linear algebra, stats, and I took calc in high school, so I need 2 other than those. Ooh. Yeah, maybe a combinatorics class. Now, actually, a combinatorics class could either be a complete disaster, or it could be really fun. I mean, I think it's a bit polarizing, actually. Is that your real hair? Yes, Mint. Yes, Mint Cubes. Absolutely. That's 100% ace. Welcome, Mint Cubes. Calc is really bad because I don't really know the theory behind stuff. I just know how to solve problems. That's a good flaw to have. Just being able to solve problems. I wish I could say that about myself. But if you're curious about the foundations of calculus, then that sounds like you want to take real analysis. As you might want to consider real analysis. Now, I should say that real analysis, Crow, is notorious for undergraduate math majors, meaning it tends to be a sort of fork in the road. it's for many people it's the first traumatic experience they have, and the issue is because of the difficulty with proving things. So if you want to fill that gap, if you want to understand what calculus was really about, you could try real analysis. Now, on the other hand, complex analysis is it has a completely different feel. That's another thing you could look into. Maybe complex analysis is something you'd like. It's all triangle inequality. Yeah, a lot of real analysis is the triangle inequality. True, actually. Very useful trick. Always used. Yeah, I agree with that. My memory is in line with Davis's comment. Yeah. So Crow, I think. Crow, there might also be a class called like Advanced Linear Algebra. That might be a math major class, Crow. You want something where you already have some background. That's another thing to look at. You could also, Crow, look to see if your school teaches something called elementary number theory or something. Something with like a first course in number theory. That could be a fun course too. It'll be very similar to your discrete math course, I predict. But it's typically a math major course. Oh, okay. You weren't so happy with linear algebra? Okay, then maybe advanced linear algebra is not your won't be your favorite subject. But you could try elementary number theory. Yeah. Oh, you didn't like it? Okay. Okay, yeah. You could try something called number theory. But be careful. Don't do any course called number theory that's not elementary. Don't ever do that, bro. Don't do that. That will be number theory is probably the hardest part of mathematics, I would say. So it's dangerous. Do the elementary one. Don't go too far. Yeah, be careful. Be careful out there. Yeah. And why? Wait. If you like discrete math, you'll like abstract algebra. Wait, I didn't think of this. You might like abstract algebra. Did you like discrete math, Pro? Okay. Then here are two classes. Okay, you like graph theory. Okay, fine. But here are two classes that you might that might be friendly for you. Elementary number theory, if that's offered. Then also the first intro to abstract algebra, or first course in abstract algebra. All right. That's the kind of thing we're doing right now in this class. However, ours is probably the first and a half course. There might be one course earlier in abstract algebra that might be easier and worth looking into. So yeah, you should look into both of those, I would say. Oh wow. Yeah, you have to like it. Absolutely. We've got a linear algebra groupie here. Yeah. Okay, that's gonna be more of a applied math class. I mean, that's gonna be... Yeah, that's gonna be an applied math class. Oh, welcome. Welcome, Mike and Ungenius. Welcome. Your name resonates with me too. Ungenius. Awesome. Yeah, Crow. Math models, if that counts, then you should do it. If you like that kind of thing. That's applied math. That's applied math. Yeah, game theory? Okay, I've seen two types of game theory classes. One type was really easy, and the other type was insanely hard. So that's one of these that you have to be careful. So I would be careful with game theory. Yeah. Okay. Ingenious. That sounds like a that sounds like some kind of plan, Crow. I don't know about... Yeah. Okay, math doesn't have the lowest GPA at all. In fact, it's relatively kind of high among the sort of STEM fields. So I was gonna say I wouldn't just cram a bunch of math classes into one semester, but I don't know. I think it's possible to cram two into a semester and hope for relatively good outcomes. Oh, I see. You want to put it all... Okay. Interesting. Yeah. That's interesting. Cool. Oh, I guess Ungenius makes it into here. Into the credits. For just having such an ingenious name. And it's weird. It's like... Okay. Alright. So Davis took 4 math classes in the last semester of undergrad. Oh, you want to be in here too? Okay. All right, you made it. You made it. Gatekeeper of linear algebra. Okay, so let's go. Let's do the credits. I gotta come up with something to say for my calc class. Right? I gotta do something. Wait, what about Davis? Will Davis. All right, awesome. Credits. Let's go. M4X. Hello. Sorry. Hello doesn't. Hello will not get you in the credits. Sorry. Sorry. It's too late. M4. Next time. Next time, you'll be in the chat early. You'll contribute, and you'll make it on the credits. Ready? Today's lecture was possible because of Tropical Geek being teacher's pet. Not saying much, but that's all that they did. And then Crow for you know, and then Sylow for great mathematics, and then my memory, and then Ungenius, and then Effie, and then Davis. All right, awesome. What's going on? We're ending stream. We're ending lecture M4X 484. But if you hit the follow button, you'll know when my next lecture is. Okay? Alright. Okay, that's not you, but thank you, AI plays things. Thank you. Alright. Okay, my next lecture is in an hour. M4. Hey, M4. I have to teach calc in an hour. I don't know any calc. I have to, like, learn it again. Like, cram it right before class. This is what professors do. M4. I'm gonna have to go do that. Oh, thanks for following. And mint cubes. Awesome. Okay, so what am I even teaching? I have no clue. What are we doing? Oh, series. Thing with series. Yeah, series. I gotta talk about series. Okay, so that's what I'm doing. Don't hog the ball. Tropical geek. That's right, Tropical. Let Crow have teacher's pet. You want a twisted cubic, AI? Here's your twisted cubic. Look at it. I just carry a twisted cubic around everywhere. Beautiful rational normal curve of degree 3 inside of space. There it is. Alright. Alright, let's get the hell out of here. Put the outro scene up. Let people leave. Alright, get out of here, people. Please leave. Hangs mate in 1. Welcome. But also, goodbye. No raid. No raid. No raid. We're just gonna do a hard, clean, swift ending.